Hi everyone, I'm Mirko Baggio. I am the Director of Business Development for Zappi Group, and I'd like to welcome you to this session. Please remember that this session is also being recorded and will be available to watch on demand following this session. If you have any questions during the session, please add them to the Q&A part. You can find that tab on the right of your screen. Note that your question will be sent privately. With that, I would like to introduce our speaker. I'd like to welcome Dr. Steffen Mutschler from Bosch Rexroth, who will speak today about empowering optimal performance with electric hydraulic solutions. Welcome, Steffen. Please take it away.
Thank you very much for the introduction, Mirko. We are today broadcasting from the Customer Benefit Center of Bosch Rexroth in Ulm. Here we have the development of our electrification products for high voltage portfolio. With this information, I would like to start into the presentation now. As Mirko was pointing out, today we want to talk about optimizing the performance of mobile machines with electrohydraulic solutions. The background for this is that we are discussing a lot with our customers about their needs coming from the change from conventional machines to electrified zero-emission machinery. What we experience is that the customers are asking many questions because there's so much to learn for all of us in the field of electrification. And one topic that comes up again and again in this discussion is how we can increase the machine runtime with respect to the battery capacity that is available on the machine. And that's why I picked exactly this topic for the presentation today, because what we do is that we look together with customers not only at the characteristics of the components that they're using. We are rather taking, let's say, full scope approach to optimize the complete machine. And of course, what can we do to increase the battery operation time? Looking at the complete machine, we can have a look at the overall machine efficiency. If we don't use the energy, then we still have it in the battery to use it for prolonged operation time. And when we talk to the customer, as I said, we look at different levels, how to improve the efficiency. So basically, there are the different levels of the machine, looking at the components themselves, looking at the complete system that we are implementing together with the customer, and also having a look at dedicated software functions to improve the efficiency to the maximum level that we can achieve. Let's go through these topics now together. We will start with a look at one very special component. Currently, we are introducing to the market our new A10VO Series 60 pump that is optimized for electric drives and also for electronic control. It is very compact and has a significantly increased performance in comparison to earlier products. This product will be available in different sizes, starting from 45 cc up to 115 cubic centimeters per revolution. And with this product, we have introduced many specific, let's say, features or improvements to design overall a completely new product here. So as you can see here, we've been working on the rotary group to increase the performance and make it as compact as possible. But also did we have a look at the housing to make it as small and lightweight as possible. And of course, on this pump that is made for electrification as well as for electronic control, we have introduced sensor interfaces so you can have pressure sensors placed on the unit as well as angle sensors to be always informed about the current displacement. In order to control this product, you have the two options to work with classic mechanical control or to go to electronic control, and by doing this, use all the flexibility that this product allows. Additionally, with the pre-compression volume that is optionally available, we can reduce the NVH on the machine, reducing the pulsation of the hydraulics, having a much lower noise behavior in comparison to conventional pumps. And this comes without any length increase, so still the product stays very compact. But I was talking a lot now about, let's say, general benefits. Yeah? If we have a look at the real improvements, you can see here in this overview that we have really done our homework. So the nominal pressure is increased, rotary speed is higher, which helps us with the electric drives, and especially the power density helps with a compact integration in the machine. But what is now today most important for us is the relative efficiency improvement that we have achieved on this new design. As you can see here, the relative efficiency goes up by a level of 7% with this new series in comparison to the previous product. Now let's have a look what this means for the electrification. So basically with this new pump, due to the sensors, we have the possibility to implement the power management on the machine, just sharing the power to the implements and, for example, the drivetrain in the right way. The increased speed helps us to reduce the electric motor size, and with a reduced pulsation, we can reduce the noise level. But the most important point again for me today is the increased efficiency. And here in the small calculation example at the bottom, you can see the impact. So basically, when we take the assumption that about 85% of our power on a certain machine is used by the hydraulics, then you can directly map the efficiency increase to this power consumption. So what this means is that the operation time, as you can see in the diagram, is increased by above 7%. Not really, it's a little less because there is always some power consumed also by auxiliaries on the machine. This was considered here. So in the end, by applying this new component, you can already achieve quite some improvement. Now let's come to the next step. What happens if I go not only in component optimization, but I have a look at the complete system. For this example, we have selected an excavator, and let me share some information about this machine. So here you can see this is our conventional wheeled excavator with a one-loop hydraulic system on it, like we used the machine for the benchmark. And you can see on the left side, looking into the pressure levels, that of course on such a machine, you have to provide the consumers with many different pressure levels, resulting in quite some losses in the hydraulic system. So let's have a quick look again, what this system is looking like. Yeah, this is the conventional machine. And basically you can see here, we have a pump, a main control valve, and with that one, we are operating the cylinders as well as the slew drive. And now, of course, we want to look into how to optimize the hydraulic system. So for this, we have many different levers coming from smaller actions, like you can see on the left top, looking into hoses and piping. For sure, you will find some optimization possibilities. You can work with flow matching to have some flow optimization, and then you can do a much bigger step, separating the machine hydraulics into a two-loop system. And you see here already, this becomes a much bigger lever, looking into different pressure levels in a range of about 20% efficiency improvement. And if you further go on, you can think about optimized slews with energy recovery, giving quite some benefit of up to 6%. And also an interesting point is to look into energy recovery from the boom, which is in our experience that we have found in measurements in the range of 8%. When you go into the second line here, you will see that you can do still much more about the efficiency going into more advanced systems. And as you can see here, there's the multi-pump system from the Purdue University going in the direction of 40% savings. There's multi-pressure network studies, which was driven, for example, by the University of Aachen, where we are in a similar range. Yeah. And so there are many different ways how you can optimize the machine. So the question is, what did we do with our excavator? Basically, as I already pointed out, we introduced in the first step two major measures on the system. the first measure was to introduce a second hydraulic pump so we can operate on 2 different pressure levels. This has the consequence that we don't have so much reducing throttle losses on the hydraulics. And as a second step, we also introduced energy recovery from the boom as well as from the slew. And then we did another step. We introduced variable speed on the diesel engine machine. And with all these measures, we achieved a reduction of the consumption by about 40%. And if you look at again, or think again about the values that I have presented on the previous slide, you can understand that somehow the different portions that go into this add up to, let's say, about 40%. The next step that we did with this machine was to introduce electrification. So the first step was really to look only at the impact of the hydraulics, but then to do the step to introduce the electrification as well. And what we did here was basically that we took our E-line component portfolios, included our electric motors, our inverters, we included our onboard charger, DC-DC converter, to set up a complete electric machine to drive our hydraulic system. And with this introduction of the electric drive, it was possible to reduce the energy consumption even further. Why is this? So as you can see on the right top side, we could apply with the electric drive a wider range of variable speed because we're more dynamic. What is helping here is, of course, the overload capability of the e-drive, helping us whenever we run into a situation where high dynamic response is needed. And what we implemented as well was a fully independent e-slew drive to maximize the energy that we can recuperate from the slew drive. So I think this value is quite impressive, right? Talking about 46% of consumption reduction. Let's have a look what this means in our calculation. So basically, when I say 46% less consumption, it means that we have still 45% consumption left. So if I take the inverse of this, I get the runtime increase of a factor 1 divided by 54%. And this means when I take the efficiency improvement that I had with my Series 60 pump, multiply this with a possible improvement by the system, I arrive at an increased battery runtime up to nearly double the value. I think this is quite impressive, but you should not forget at this point that this is for sure due to the high portion of energy on the machine, I assumed 85%, that is used by the hydraulic system really. But then we were looking even deeper and testing the machine not only with one operator, we wanted to understand how big is really the impact of the operator. Is it the same for every machine operator or does it change? And then we gave the machine to an operator that is less experienced. So here you can see again, the result with operator 1 was to reduce the consumption by 46%, while with operator 2, we only achieved 38%. So this was for us a little, let's say, discouraging, because in the first moment, we did not really understand how the differences can be so big. But then we looked into what the operator is doing, and we found out that the most important topic about this is taking care of avoiding the end stops. So from this point, we thought about what we can do about it. But now let's first have a look at the impact of this untrained operator. So if we have a look at our energy or operation balance again, with the less trained operator, we have only about 38% savings, meaning the consumption is not down to a level of 54%, but rather only down to a level of 62%. And this means that with this less experienced operator, we only achieve 170%, 171% of increased battery runtime. So what we thought about this is what can we do? And the clear step that is a way to support here the situation to improve the result is to introduce assistance functions. So basically, with the introduction of assistance functions, after understanding what is the reason for the reduced operation time, we were able to again increase the operation time to a similar level as we had achieved with the experienced operator. I simplified it here a little. I just wrote a full consumption of about 25% on the operation time. Yeah, but I must admit, we did nearly get there, but not completely, of course, as there's always a human factor in it. So I think this is quite impressive what you can reach on the system. Now let's also have a look at the software. So which levers do we still have to improve the machine efficiency looking into software functionality? And basically here for us, one topic that is quite in the focus is how to operate pump and electric motor in the best way together. Basically, when we are talking to customers, there's a lot of experience out of the combustion engine field. So basically, we are saying it's a rough value that typically everybody would agree on. If you reduce the engine speed to, let's say, a maximum reduction that is possible, you end up somewhere between 10–15% reduced consumption. Yeah? And this is the assumption that many of our customers also take into the electric machine. But then when we start the discussion, we have a look together at the electric drive. And you can see that a similar speed reduction on the electric drive does not improve the efficiency of the drive unit by about 10%. It rather has a negative impact on the efficiency. So for sure, there's some space for optimization, yeah? Especially when you look at the topic with the even higher complexity of taking also care of the hydraulic pump. And basically now for a zero emission machine, we don't need to look anymore at the combustion engine. So let's have a look at the efficiency maps of the electric drive and the hydraulic pump. And we can see that we have here contradicting requirements. So basically reducing the speed helps a lot to increase the efficiency of the hydraulic pump. But at the same time, you are reducing the efficiency of the electric drive. So what we have to do here is to think about optimization of the efficiency of the operation point to come in the end to the best result. And what can we optimize here? Let's have a look at the pump and electric motor functionality together. So basically what we need on the machine is a certain pump flow. As you can see in the diagram on the right side, we have the rotary speed on the y-axis, we have the displacement of the hydraulic pump on the x-axis, and the product of both leads to a certain flow. As you can see on the right-hand corner, there's a curve of an equal flow. And basically now the question that we have to answer is, how do we realize this equal flow in the best way? Is it beneficial to increase the pump speed, or is it beneficial to increase the pump displacement? And this is a question you have to answer not only once, but you can answer this question in every millisecond of the operation. So we have implemented an optimization algorithm in a software solution package. What we are providing as a complete solution, you can see here on this slide. So basically, we have our control unit. On this control unit, we could have the complete machine control, asking for a certain flow and giving a certain power limit. And then we have the Sitronics software package. This package optimizes the pump and motor operation for the best efficiency, if this is what you want, or it optimizes for the best sound behavior or the best dynamics. This is all included in our Sitronics package. With this software package implemented on the controller, we are then controlling the electric motor via the inverter, and we are controlling the hydraulic pump to always deliver together the best flow. And now you can think about, does it really work? Yeah? Which improvements does it really bring? And of course, we had a look at this. So as a basis, we are again looking here at an excavator, and we did measurements in different load conditions. So on the left side, you can see the time measurement of flow and pressure. We were operating in a high power mode at low load and also in a, let's say, standard mode of the machine. And on the right side, you can see then, let's say, how this is reflected in the delta P flow map of the drive. And this is exactly where we have to optimize to come to the best efficiency. The result of the study, I can directly share with you, because first we did a simulation. So on the left-hand side, you can see the advantage we achieved in the simulation. So basically, we have the combination of all three different operation modes, and then we have measurements separated here also, or let's say values here in the simulation, separated for the power mode, for low load operation, and for the standard mode operation. And you can see already here from the power mode operation, we had, let's say, the smallest improvements in the efficiency, while in low load conditions, the efficiency impact is quite high. So with this information, looking at your application, looking at your use cases, it helps to understand what can really be the benefit for your machine. We were looking here at two different strategies. The blue one, it's a minimized speed, and the dark blue one, it's the optimized speed operation. So you can already say from the simulation that reducing the nominal speed as much as possible, like we do with the diesel engine, it's not leading in the wrong direction. It's already helping a lot. And however, you can see that you get more benefit out of it when you go to an optimized operation strategy. And here it's interesting that the difference in the low load condition is not so high. But when you have power mode operation, then you really see the optimization of the speed is beneficial and takes you in a full power mode operation into a range of 2% efficiency improvement. On the right-hand side, we have more or less the same data as it was confirmed by our test bench testing, where we, in the end, were working on the same pressure and flow levels and working with real components to see if the results that we achieved in the simulation are, let's say, correct. Now, as a conclusion, based on the machine usage, you can achieve between 2 up to even 9% for low load conditions with optimized control. And I think this makes it quite interesting. And why is it so interesting? Because in the end, we are talking here about software. This has no impact on the selected components. This has no impact on the system costs. Yeah, of course, the software functionality needs to be developed, needs to be implemented. There are efforts related to this, but it's, from my perspective, quite a smart way to take out all the efficiency of the system that you can achieve. Now let's see what this means on the complete machine level then. If we now take this into consideration again, so what did I do? I have an average value of about 3% efficiency improvement for the subsystem inverter, motor, and pump with the optimum control. But 1.5% of this were already considered in our systems measurement that the colleagues have done. So in the 46% consumption reduction, we were already working with the N-min strategy. That's why here in this, let's say, calculation, I'm not considering the 3%, I'm only considering about, let's say, 1.5, 2% that you can see at the bottom. And this takes us overall to an increased battery runtime for the complete machine of nearly twice the time. So when you ask me again how to increase battery operation time, I can tell you we have the different levers that we need to consider on the complete machine, looking into the selection of optimum components, looking into potentials in the system, and of course, understanding what is the impact that we can have with software functions. At the same time, we need to consider the impact of the operator. and probably react with assistance functions to compensate for, let's say, negative impact that can be caused by untrained operators. So in the end, with our E-line solution, in total, it's possible to increase the machine operation time significantly. Thank you.
Okay, thank you, Steffen, for your very nice presentation. So I think we have time for some questions. So the first question I see here is, when is the new A10VO Series 60 available?
The first nominal size, 45 cc, is already in series production, and we will continue with the other sizes, let's say, this year and the following years.
Okay, thank you. So next question. The battery runtime increase you show is impressive. So yeah, do you think it is possible to get in any machine type?
Yeah, that's a very good question. Yeah? Because in fact, Mirko, the topic is that I have selected here a use case of a machine where the hydraulic portion of the energy consumption is very high. Yeah? If you look into other applications or other use cases where you have a high portion of travel driving, for example, then the implement system does not have such a high impact. Yeah? However, what we do always is to look at the overall system to understand where we have, let's say, the biggest levers to improve the overall efficiency.
Mm-hmm. Yeah. Okay, so next question. Thanks for sharing this example, but how can I ensure to select the best solution for my machine? I think it's a little bit connected to the previous question in a way.
Yes, exactly. So basically what we do is that we look together with the customer into his machine application, understand together what are the duty cycles, and based on that, we have a simulation tool. So basically the customer can provide to us flow and pressure requirements, and with these requirements we can run simulations to understand which electric motor is the best, which pump selection is the best one. Does it make sense to use a variable displacement pump, or should we rather use a fixed displacement pump? Yeah. So in this way, together with the customer, looking at the application, we are always working to find the best solution.
Okay. Yeah, and this maybe is answering also the next question regarding if the algorithm that you have inside the electronics are standard or can be in some way customized based on the vehicle type or the customer request, but basically I think you have already answered.
Yeah, maybe I can say something about this. So basically, with the development of the Sitronic solution, we have a very long experience in the field of industrial applications. So we started about 15-20 years ago already to work on these algorithms. And with that experience, it was a task, let's say, to transfer the algorithms from industrial applications where you have a lot of computing power to mobile applications. Yeah.
Okay.
And for sure, this was one of the major tasks. And of course, we can adapt the software always, let's say, to the hydraulic system and to the electric machines that we are applying.
Okay. Oh, I have a very interesting question now. In conjunction with electrification, to increase the electric motor power density will be a benefit to run high speed as much as possible.
Yes.
So are you working in higher speed solutions, I guess, for the hydraulics, like 5,000 RPM or more?
This is an information that I cannot yet talk about today. Okay. You will see in the future what is happening.
Yeah, and I mean, personally, I am really interested in this question because, you know, who wants to develop motors, they want to go higher and higher in speed. So
yes. Yeah, so generally this is possible, but of course you have to take certain measures to make it possible, in the pump technology and also in the system. Yeah.
So many questions are coming, I tell you. So this is asking if there are some impact in these new technologies, these new solutions on the after sales and field service. So maintenance or other stuff like that, what is the impact?
That's a challenging question. I believe the biggest impact here is that in the field of service, we need to increase the competencies for software and high voltage technology. Yeah, I think this is one of the major impacts that we see currently, that with any new development in this direction, we have to take care to train our service teams to make it possible for them to analyze the machine on site and to take the right measures to help the customers.
Okay, so next question. If we increase the motor speed for better efficiency, do you think that the system noise level will increase too? Because it is a serious matter.
Yes, and that is, of course, always, let's say, the different optimization goals that you have, right? So if you have a need for a really silent machine, maximum speed is probably not the right approach to realize this.
Okay. So next question, which recuperation vector did you choose to reach 6% with slew and 8% with boom? Simply hydraulic or also electric?
This was done on the hydraulic machine. This was without the electric slew.
Okay.
And maybe here's one interesting point. If you recover energy or recuperate energy hydraulically, then you can reuse it in the hydraulic system. And this is sometimes even more efficient than transferring it to electric energy first and then bringing it back to hydraulic energy. So we had quite some interesting finding here, that it's not always the best to use electric drives for energy recuperation. Because of transferring it from the different, let's say, regimes, from hydraulic to mechanic to electric and back again.
Since hydraulic savings shown were around 40%, and then after electric drive, the savings were 46%. Would you say that to achieve energy savings, focusing on hydraulics is better approach than looking at electrics? I think it's more or less what you were saying.
Yeah, I can add something to this. So basically, it depends always on the machine function. When you're talking about the hydraulic system of the machine, implement hydraulics, for example, then there's a huge lever in the hydraulic system. When you're talking about a travel drive application, of course, it makes sense to look into the efficiency benefit of an electric solution. And the slew drive is something in the middle. So you really can look into the application to understand the duty cycle, what is the best solution here. But we have some indications that the hydraulic solution with energy recuperation from the slew drive is also not so bad in comparison.
Okay. So next question says, simulation seems to be very precise today. So are there, in your opinion, still improvements possible?
In the end, this is all about model validations. So basically, if you have a good knowledge of the product and you can make a very good physical model of the product, at the same time you have the real product available to do a, let's say, a parameter study to understand which is the right parameter setting for your model, then you can achieve a really very good level on component side. And combining very good component models to a system model typically then leads to a good result.
Yeah, sure. Another question, what changes in hose size do we need to do, and how significant the effect is that?
Yes, so at this point it depends, of course, always on the application, which flow you have, how you select the hoses based on that, and it's the best to optimize this with a hydraulic hose supplier to see together where you have the optimum for the application.
Does your control box operate with the e-mechanical PTO supplied by the truck manufacturer?
Generally, this is possible.
Yeah.
Yeah.
A calculation was made to understand what difference there is between a traditional system and this one in terms of energy cost. In 8 hours of work, what is the cost of the standard fuel solution and how much is the energy cost with electric?
So for this, I don't have the calculation here on hand,
Yeah.
but there's one impact that is quite interesting from my point of view. That is the impact of where you operate the machine. So today in Germany, electricity is very expensive, and also fuel is quite expensive. If you go to France, you have different relationships between the costs, yeah. And if you go to Saudi Arabia, it looks again different, yeah.
Yeah.
So that would be a first step to talk about which fuel and energy prices we are talking about. And of course, it makes sense to consider this complete calculation for a return of invest approach in the case you do not really need zero emission for your site, but you look for the most economic machine solution.
Mm-hmm. Okay, I have the last question here. What do you think about having same pressure at every function of the machine in order to reduce the losses when multiple functions are used?
Yes. So I like this approach as a, let's say, provider for valves and pumps, but we are here in a conflict with the suppliers of the cylinders. And typically the customer is looking for the most cost-effective solution. Yeah. And here we have in the end a clear contradiction.
Okay. No, another questions came now. So do you see the market moving to voltages above 1000 volt when MCS replaces CCS in charging infrastructure? If yes, then are the E-Lion products available for it?
That's an interesting point. So for the mobile machinery, I do not yet have any indications to go to voltages above 1000 volt. We see it sometimes in the requests for the truck market though. Yeah. So whenever we are close to on-road applications, we see that this can be for sure a future trend. Are the E-Line products available for it? Our maximum voltage for the inverter is 850 volt. So today, the E-Line products are not the right solution to go above 1000 volt.
Okay. Okay. Thank you for answer also these questions. We had a lot of questions today.
Mm-hmm.
Good. That it means that you have stimulated the audience. And yeah, as I said in the beginning, it's possible to watch also on demand this session. And yeah, at this point, I will thank you again, Steffen, for today. And see you soon.
Very good, Mirko. It was a pleasure. See you soon. Bye-bye.
Yeah, bye.